So in section 5.7 we continue with using the definition of the definite integral as a limit of a Riemann sum. So just for a moment, let's remember this is the Riemann sum. In section 5.7 we continue to work with the new limit definition of the definite integral. It is the limit of a Riemann sum, and this is what we call a Riemann sum. So let's just review for a second what that is. You have a function f of x drawn over an interval a b. We don't see the a and the b here, but we have chopped the interval up. The interval AB has been partitioned into n subintervals, and over each one of those subintervals, k equals the first one, k equals 2 is the second one, k equals 3 is the third one, we're picking a sample point and evaluating the function at that sample point and multiplying by delta x. And you remember delta x is the width of the interval AB, b minus a, divided by n, the number of subintervals. One of the reasons this definition is so useful is because in the physical sciences, in economics, chemistry, there are lots of quantities that scientists can estimate the total quantity by breaking it up into small pieces and having a known formula for these quantities over very, very small intervals. And so then they want to add these up and recognize that it is a Riemann sum, and so they can actually find the total amount of the quantity that they're calculating by just taking a definite integral. So we want to learn how to recognize Riemann sums, and to, instead of trying some crazy thing like trying to actually take the limit, which would be almost impossible because that sum has an ever-increasing number of terms. So unless you can collapse that sum into a known formula, you really can't take the limit. But we can recognize it as a Riemann sum and calculate it as a definite integral. Some examples of applications of this are finding areas in the plane, finding volumes, arc length, the amount of work done by a varying force in physics, electrical energy needs, profit, and distance traveled. We have an example in the book of that. And we're going to do volumes, arc length, and area after we finish this section. Now, here is a picture of the interval AB, and I have partitioned it into n subintervals. This is by far the most important thing in this lecture, so really take time with it. Notice we call x sub 0 a, and, well, right off the bat I have a mistake here, wouldn't you know? This should be x1 and x2. So we have x naught or x0 equals a, then x1, x2. The little red hash marks mean, and it goes on, and then we get to the arbitrary subinterval, the kth subinterval. And it's x sub k minus 1 comma x sub k. Right here is the kth subinterval. Notice that x1 is the right endpoint of the first subinterval. x2 is the right endpoint of the second subinterval, and likewise x sub k is the right endpoint of the kth subinterval. And then, of course, the last one, before b, is x sub n minus 1, and then x sub n is b. So that's the partition. Now, in each one of these subintervals, we want to choose a c sub k. We want to choose a sample point C1 in the first subinterval and C2 in the second, and so on. But just picking them arbitrarily won't help us with what we want to do. So we want to learn how to pick these sample points systematically. In other words, pick a right endpoint, a left endpoint, or a midpoint. And if we do that, we'll be able to write the Riemann sums. We will even be able to program a Riemann sum into Mathematica if we have formulas for the C sub k. So let's see, how would we do that? Well, if we're picking right endpoints, let me put right Riemann sum. If we were picking right endpoints, let's see how we could get a formula. x1 is, let's see if I can write this. x1 is a plus delta x, isn't it? And delta x is b minus a over n. x2 is a plus 2 delta x's. Notice a plus 2 jumps of delta x. x3 would be a plus 3 jumps of delta x, and so we have a formula for x sub k. A plus k jumps of delta x. And for that matter, we have a formula for x sub k minus 1. A plus k minus 1 jumps of delta x. And of course, x sub n minus 1 is a plus, a plus n minus 1 delta x's, and b is a plus n jumps of delta x. But the ones we want to focus on are these on the kth subinterval, because then we can just let k go from 1 to n, and we have it on all subintervals. So let's see. If we're choosing right endpoints, again, if we're choosing right endpoints, our Riemann sum will be the sum from k equals 1 to n. And all I have to do is express f of c sub k on the kth subinterval times delta x. So it would be our function. We'll just use f of a plus k jumps of delta x. That's the right endpoint of the kth subinterval times delta x. And that gives us our right Riemann sum. Now, delta x is b minus a over n when we're actually doing a problem, but we'll just leave it like this for now. Now, a left Riemann sum, we could write it as the sum, well, here, I'll write it both ways. The sum from k equals 1 to n of f of a plus, in parentheses, k minus 1 jumps of delta x times delta x. But there's a more simple way to write it. Instead of starting our counter at k equals 1, we could just use the exact same formula we have for the right Riemann sum, but start our counter at a plus 0 jumps of delta x, and end it at x sub n minus 1. So in that case, we do the same. We have f of a plus k delta x's times delta x, but we start k at 0 and end it at n minus 1. So this one is the easier one to remember. The main thing to remember is this drawing up here. Right here. How do you find formulas for the left endpoint, right endpoint, and midpoint? Now for midpoint, I think I'll do in yellow. The midpoint, if we want to choose the middle of each subinterval, the midpoint as c sub k, we need a formula for it. Well, it's going to be a plus, now let me do it this way. I'll go a plus k jumps and back a half. So a plus k k minus 1/2 times delta x. A plus, jumping over k jumps of delta x and backing up minus 1/2. Minus 1/2 of delta x. So our midpoint Riemann sum will be, let me make this go down a bit. Our midpoint Riemann sum will be the sum from k equals 1 to n of f of a plus k minus 1/2 jumps of delta x times delta x. Now, if you just memorize this part up here that I have circled in white here, actually all you really need to know is the midpoint and the right endpoint. And it's so easy because you can always just draw this out and think, oh, right endpoint, a plus 1 jump of delta x, a plus 2 jumps. Okay, that would be a plus k jumps of delta x, and I have to back up 1/2 for the midpoint. So, assuming that you have taken a little bit of time to really look at how we form that systematic, or the systematic method of forming a Riemann sum with the right endpoints, midpoints, or left endpoints, we can do some problems. This one, explain why the limit as n goes to infinity of this sum. Well, it must be a Riemann sum because the limit as n goes to infinity is a definite integral. We want to prove it is. So we have to figure out what is the Riemann sum. Well, the first thing we can see is that the function is x cubed because we see this is cubed. And if this is a right endpoint, which it appeared to be, a must be equal to 4 because we see that 4 plus k times 1 over n. Oh, and here's 1 over n here. So this 1 over n could be written, this could have been written this way, k equals 1 to n, 4 plus k times 1 over n, cubed times 1 over n. Notice k is what's changing in this sum, not n. N doesn't change until you take the limit and let it go to infinity. So when you're just looking at the Riemann sum, this 1 over n doesn't have anything to do with k, and we see our author quite often just factors it out of the sum and puts it to the left of the sigma sign, the summation. That's because it doesn't involve k. So we can see that delta x indeed is 1 over n, and that this is 4 plus k jumps of 1 over n being summed from 1 to n. So this is a right Riemann sum. And what would b be? Well, b minus a, b minus 4 over n, equals 1 over n. That's our delta x. So b clearly is 5. So I'll put b equals 5. And that does it. Once we have f, a, and b, we're really done. This is the integral from 4 to 5 of x cubed dx, which is, you can easily calculate this. I got 92.25. The next problem is number 30 in your text. Explain why, again, another sum here. Looks like a Riemann sum. In fact, k goes from 0 to n minus 1. This looks like a left Riemann sum, doesn't it? And this part here, well, it's the square root, so that's easy. F of x is equal to the square root function. This is a left Riemann sum for f of x equals the square root of x. A is equal to 1, and this must be a plus k jumps of delta x. And you see the delta x is factored to the left of the summation sign again, and this here is k times 3 over n. So delta x is equal to 3 over n. And 3 is b minus a, so this together gives us the fact that b must be 4. And there we go. This is really all you have to do. You would say in answer to this question that this is a left Riemann sum for the function square root of x with a equals 1, b equals 4. And you're done. That proves it. Question 41. Evaluate this limit by expressing it as a definite integral and then evaluating this integral using the fundamental theorem of calculus. Well, we certainly could not evaluate that limit as is, because as n goes to infinity, the sum keeps getting longer and longer and longer. In other words, the expression that we're taking the limit of is not in closed form, as we say. It's not there's no formula with n in it that we could take the limit. So we need to express this as a definite integral. Well, j is going from 1 to n, the counter. So, and inside here we see, that a must be 0. And the function is the cubing function. So again, f of x is equal to x cubed. And we could write this as, notice this part here could be written as 0 plus j jumps of 1 over n cubed. And sure enough, 1 over n is delta x. You can see it sitting right here. He factors the delta x to the left all the time. So this looks like a right Riemann sum. The counter is going from 1 to n. It's a right Riemann sum for this function. A is equal to 0 and delta x is 1 over n. Together that gives us b is equal to 1. So I will evaluate this limit by saying this limit is equal to the integral from 0 to 1 of x cubed dx, which is, well, 1/4. X to the 4th, evaluated from 1 to 0, gives us 1/4. We took this limit. The limit of that complicated looking sum is simply 1/4, because we could evaluate it as a definite integral. Well, now this next one looks even more complicated. K is going from 1 to n. We're hoping that this is a Riemann sum because we couldn't evaluate the limit unless it is. Well, it looks to me like delta x would be 3 over n, because I see this here. So if this is a Riemann sum, we know that b minus a over n is delta x, and that it could be factored out of that product, out of the sum, each term. Okay, so let's look. If a is 1 plus, so a is 1. And if delta x is 3 over n, this gives us b is equal to 4. b is equal to 4. But let's double check, what kind of sum is this? Well, if I write that square root this way, 1 plus, now delta x is 3 over n. So 3 over n. And what is left? Well, that's 2k minus 1 over 2. Oh, well, that's just the midpoint. That's 1 plus k minus a half jumps of 3 over n. You don't have to write it the way I wrote it, but this is the way I did on that slide where we studied the systematic way of writing a formula for the right endpoint, the left endpoint, and the midpoint. So our function is the square root function. And we can evaluate this by recognizing it is the limit of a Riemann sum for the square root of x over the interval from 1 to 4, which if you evaluate it, you will get 14/3. So that's the limit. Notice that's the same integral that we did in example 2 using a left Riemann sum. Now this problem is different. This asks us to evaluate the definite integral of x dx from 0 to 3 by computing the limit of right sums. Of course, if you were just interested in getting the answer, you would simply 1/2 x squared evaluated from 3 to 9 is what? 9/2. So we already know what we're going to get, 9/2. This is just an exercise in showing you how to compute the limit of a Riemann sum. Most of them we can't compute, but this is one that we will be able to. In fact, I thought I had the formula. Yeah, there it is. I'm sure you have seen this before. It's one of the standard little formulas that you prove by using induction, that the sum of the first n integers or natural numbers is n times n plus 1 over 2. Now, what you notice here, if you write a sum this way, or another way, sigma k from k equals 1 to n, that is in open form. It doesn't have a closed form to it. Every single sum gets longer and longer and longer, so it's not something we can take the limit of. But this particular sum has a closed form. It has a formula for the sum. Now here we can take the limit of some expression with this involved in it. We have a chance of taking the limit, just as you did in Calculus 1. So let's first of all set up the right Riemann sum. We're going to sum from k equals 1 to n, right Riemann sum. The function is just x, and a is 0. 0 plus k jumps of delta x, which is 3 minus 0 over n, 3 over n, times 3 over n. Alright, so I guess bring the 3. Actually, this is, look, it's the sum from k equals 1. When the function is just x, I can multiply those. It's k times 3 times 3, 9 over n squared. And this does not involve k, so I can factor it out of each term in that sum of n terms. So I'll bring the 9 over n squared to the left, and what I have here is the sum from k equals 1 to n of k. Well, that's exactly, that's exactly this sum here, the sum from k equals 1 to n of k, and we have a formula for it. So I'm going to replace this sum, 1 plus 2 plus 3 plus 4, etc., up to n, with the formula that we are given. 9 over n squared times n plus 1 over 2. This is a closed form, and I can take the limit. The limit as n goes to infinity of, well, one of these n's cancel, so let's write 9/2, and one of the n's canceled, so we have n plus 1 over n. Now you know that n plus 1 over n approaches 1 as n goes to infinity, so this limit is equal to 9/2, exactly what we knew we should get. You won't have to do many problems like this because usually there's no closed form. We do have a closed form for the sum of k squared and one for the sum of k cubed, and those are in your textbook. You could see them. You certainly don't need to memorize those formulas.